Hello and welcome to today's session on advanced analysis with NIQL for analytics. This will be a joint presentation with Dimitri. So what we're going to do today, so we have two sections here. The first section, I will cover that, and the second section will be covered by Dimitri. The first section is really about NIQL for basic JSON querying and manipulation. And so we'll talk about a little bit about differences between SQL and NIQL. And I will also talk about basic aggregation and grouping. So let's get started with that. So before we get started with queries, let's look at the data. So the data is a simple data set that we're talking about here that we will use in a number of the examples. So what you will see here, you will have a collection that's called stores. And you see in there that you have an address field and a categories field and three more fields further below. And the one thing that you will see here is that the address field has nested other fields, the city, the street, and zip code field. So, which is kind of uncommon for SQL, but of course very common for JSON, which we are using. So, but that's a difference that needs to be addressed in processing as well. And the other field that we see is the categories field in yellow here, and that also is nested, but it's nested in a different way. So here we basically get atomic values that are nested within an array and not within an object as we have above. The other collections that we have here are the stock by collection, which is basically just a connection between the stores and the products that we see on the right. And so that's kind of the first half of the data sets and that we're using here. And then there are two more collections here. One is a users collection. Again, you will see some nesting here, and an orders collection. The interesting thing that you will see here about the data is that you see, if you look, for example, at the orders collection in the middle, you will see that there is a red field in there, and you will see that on the right side, equivalent to that, there's another one, but they have different names. So basically, there's a field that exists only on the left side, and there's a field that only exists on the right side, which is also a little bit uncommon for SQL, but very common for NIQL. So as I start kind of with these data differences, let's start on the query side with something that's very familiar. So let's look at a simple query that you might be familiar with if you do SQL. So it's very simple. You want to select the email and the time and order was placed from the users collection that you join with the orders collection on the user ID. And you just want records where the total price of the order is greater than 200. And we'll order that by the price, and we'll limit it to 3 so that it fits on the screen. And so you see the result of this on the right side here. It's just looks like a regular tuple, with the difference that it's in curly braces instead of kind of a tabular arrangement. But yeah, this is, you have a regular SQL query, you get a regular SQL result, everything is good. And as we'll see soon, all of SQL basically works, but we also are generalizing it to support a little more things like the nesting that we have here. So, as I said, you have nested data, and so what happens is if you want to work with the nested data, sometimes you need to unnest the data to get to a flat representation that you need. And so in this example here, we want to get the order ID and the user ID from an order. And then for each item that we have in the items that were in the order, we want to have a separate row or a separate record. And so that's why we need to unnest the data. And what we see here in the from clause, you see orders O unnest O.items, which means that we're unnesting the items within the orders and so get this flat representation. And so the result of this query, as you can see here, is what you see on the right. So you have the order ID and the user ID that you got from the order, and then we kind of pulled up the product and the quantity from the nested items array, and so that basically now we have a flat record again, which is what you would have in SQL. But it's just very useful in general to be able to do these transformations this way. So we basically introduced this as getting from orders unnest O.items on the left. There is a slightly more elegant way to express that, and the slightly more elegant way is to just use a comma here instead of this keyword. That will basically have the same result. What we see here is that we have a left correlation between the variable O on orders and O.items. So basically the O is the same on both sides, and we kind of do something like an implicit join here between the orders and the items. Okay, so now we have looked at this unnesting, and that's something you can do to kind of get back to a flatter structure. But of course, you can also deal with nested data in a query. So one thing that you would like to do, for example, is that you can have predicates on that. And the typical predicates are that you want to find out, for example, if something is true for the items in a collection. And so in here we have this query, we take the orders, and from the orders we want to get the user IDs, where there are items in the items array where the selling price is greater than 80, right? And so basically we write that as where some I in o.item satisfies that the selling price is greater than 80. And we get a result for that, and that you see on the right. Now, you can also do something else on the collection, basically, where you say, okay, actually, I don't want to have get the IDs for everything where there's at least one that qualifies for the condition. Instead, I want everything in the items array to qualify. So then basically we have a slightly different formulation. Instead of some, we use every here. But otherwise, it's largely the same. So we run this query, and we get fewer records, which is somewhat expected because the likelihood that all of the values are in the nested array is somewhat lower. And then there is one kind of usual challenge that we have here is the case when actually the actual container, the array, might be empty, in which case it would be trivially true that every item, because there is no item, satisfies the condition. So sometimes what you need to do, and that's usual in most programming query languages, you would need to also verify that actually you have at least one item in there to understand that you really satisfy all the items that are there. And so that would, in this case, we just did that by adding this array count, where we count the length of the array, of the items array, and we validate that it's greater than 0. And so these are very typical predicates that you use in a nested data model. All right, in this specific case, the query result is the same as before because we didn't have any items that had a selling price greater than 70 but didn't fit in here. Okay, so with that, let's take a look back here at the data. So I talked a little bit about the red fields here before, that basically you have different fields in different places. And so now let's look a little bit more in detail what that means for us in the query language. So suppose you have a query like this one. So you, from the orders, you want to get the order ID, the time the order was placed, the time it was fulfilled, the price and the user ID, and you want to find that out for all objects where the total price is greater than 150. And you only want to do that for orders where the time fulfilled is actually missing, which means that the order was actually not fulfilled so far. So what you see here is interesting. In the select clause, you will see 5 fields. However, if you actually evaluate the query, you will only see 4 fields for each of those records. And so the reason, of course, is that the time fulfilled field is missing, and we actually chose our query in a way that this is missing, so that all the records that we're getting don't have this time fulfilled field. And that is somewhat different from what you would usually expect in SQL. In SQL, if a value is not available, you would expect it to be null as an indicator, and that way you would keep the same width of the record. However, this is a little bit more precise, especially in a data model as we have, where you don't have a fixed schema. So this is expected here, but it might be the case that you actually did want to get the full width, and then of course you can still do the regular things that you would do in SQL. You could create a field like we do here and have, for example, a case statement to provide a value to the field even though it's missing. And in this case, what we're doing is if the time fulfilled is missing, then we'll enter a string that's called TBD. And otherwise, if there is a value, we'll just get that value. So that's kind of a way how you can deal with the fact that you have a different width for the records if you're not looking for that. Okay. Yeah, and so this is basically, this is the result for the query that I just mentioned. You see here the red field is time fulfilled is TBD. That was what we got. Okay, so now let's move on. So basically we talked about analytics, and one of the important parts really when you do analyses often is that you need to do aggregation. And so let's take a look at how aggregation works in NQL. So one of the interesting things about aggregation in NQL is that you can actually separate aggregation from grouping. So in SQL, you can only use aggregate functions to aggregate the content if you also have a group by clause that allows you basically to create those groups over which you then aggregate. In NQL, that's different because we actually have these nested objects. And so if I wanted to have this query where I take I join my users and my orders, and then I want to get the email and the number of the orders that I have in this order, the number of items in the order. So then I can simply do this simple query, right? I mean, it's for each record, we have a number of items in the order, and so we just count them, and then we get the result. And so in this case, we have these 3 results, and with different order sizes between 7 and 8. Another aspect that's even more interesting is that not only can you do aggregation without grouping, but in NQL you can also do grouping without aggregation. And that is quite an interesting concept. So let's look at this query. And so what this query does, it takes the stores and the orders and it joins them on the store ID. And then we group them by the state, right, of where the address is in. And then you see a new clause that you're probably not familiar with, which is the group as clause. So what this does is you will get a variable binding for G for the whole group, basically, which gives you the whole grouping of the data that you're joining here. And so to see what that looks like, let's take a look. Here's an example. As you see in this group variable, what you have is a 2 fields at the top level. One is the state, which is what we selected in the select clause, and the other one is G, the group variable, which we also have in the select clause. And this group variable has an interesting structure. So what it contains basically an array of objects, and the objects are the individual pairs of stores and orders that belong together. And so in this case, the first thing is we have the state, that's at the global level, that's for Arkansas, it's AK. And then inside of the group variable, we have the store, and we basically have the full store record there with the store ID and the name and the address. And on the other side of this, we also have the full order on the right side that you see here in green. So basically, both of those records that have been joined are available in their full size in this variable for further processing. And as you can see, we are using, for the field names here, we're using the names of the variables. So that allows us to disambiguate the source of the data. And so this is now, this is a very interesting concept. So basically you can actually look at the whole group, but it's also kind of involved and pretty big, as you see here. That's probably not what you really want. But what you can do is you can run an arbitrary subquery on this group variable. So basically what we're doing in this case, we did the same as we did before, right? We're joining the orders and the stores, but then we only want to retrieve actually the store ID, the store name, and the order ID. So we only want to have these 3 pieces of the grouping variable, and then we can get a nice result. I mean, the interesting thing is this can be any query over the group, right? But this is a relatively simple one, and we can just get a result that looks approximately like this, no, precisely like this, where you have the state and then just the store ID, the name of the store, and the order ID, which is exactly what you were looking for. So with that, there's actually one very interesting thing also from a theoretical perspective. So if you run an aggregation query or a grouping and aggregation query in SQL, then it looks something like this, what we have here, right? So what we do is we join the stores and the orders and again on the store ID. Then we group by the address state, and then we have a count star, which is a specific aggregate function to give us the number. Sorry, to give us the number of stores in the state. And so this is interesting in that you kind of cannot separate these two. I mentioned that before, right? You either have grouping and aggregation in SQL, or basically you cannot only have one of the two. In this case, since we have just shown you how you can separate the grouping and the aggregation, we have a very simple explanation for what this actually means in terms of the data model. And namely, it is the query that we see down here. So what we're doing here is, again, we do the same as we do above. We join the stores and the orders, and then we group them by the state, and then we get this group variable. And the count that we have above is basically just the size of the group variable, right? It's the number of records that are in the group variable. And so basically we just can write this down as array count of G, and we'll get exactly the same result. Okay. So I hope that gave you some insight over kind of the slight differences in the data model and in what you can do processing-wise between NICL and SQL, so kind of what extensions are available. And with that, I would like to give it over to Dimitri to talk more about the details of the analytical features that are mostly based on grouping and aggregation.
Thank you, Till. I'm going to talk about advanced features of NICL for analytics, grouping sets, window functions, and user-defined functions. So these features have been supported in standard SQL for a while. Grouping sets were introduced in SQL 99. They extend group by clause to allow aggregation over multiple dimensions. Window functions appeared in SQL 2003. So these functions enable aggregation over windows computed on the input data. We've been supporting window functions since 6.5 release of Couchbase Analytics, and grouping sets since our most recent 7.0 release. Let's start with discussing grouping sets and related rollup and CUBE modifiers. Then we move on to various window function calls and go over some examples using those. Grouping sets have been supported by major relational database systems. They're used for advanced analytical queries that aggregate data over multiple dimensions. Couchbase Analytics 7.0 release now supports them as well. Let's look at the following query. We would like to count the number of stores in each city in each state. To limit the result, we would only consider states with names starting with letter C. In addition to counting by city, we would also like to get a total count by state and the overall count of all our stores. So how do we do that? One way of implementing this would be to do a union all over 3 subqueries. The first subquery would group by state and city, the second would group by state, and the third one would just do select count star over the whole dataset. This approach works, but requires some code duplication. With grouping sets, we have a better way. We can simply use a rollup modifier in the group by clause. If you look at the box on the right, you'll see 3 different formulations of the same query. The main actor here is the grouping sets modifier in the middle, which provides a compact way of specifying those unions. Each grouping set is logically expanded into a separate subquery, and they're all connected by union all operations. So the grouping sets modifier is a shortcut for union all, but the rollup modifier is a shortcut for grouping sets. Rollup with n elements is expanded into n+1 grouping sets, rolling up to the grand total. In our query, we start with a rollup with 2 elements, state and city. Therefore, it would expand into 3 grouping sets, city with state, the whole state, and the grand total. And that's exactly what we want in our report. If we look at the query results, we'll see black rows that correspond to grouping by city, blue ones for the whole state, and the red one for the grand total. CUBE modifier is a relative of rollup, but performs a slightly different expansion into the grouping sets. In this example, we want to find out our total sales by each year within each state. In addition to that, we would like to roll up by year, also roll up by state, and get a grand total. That's what the CUBE modifier is for. It can roll up by multiple dimensions. Contrast this with the rollup modifier we discussed earlier, which can only roll up by a single dimension. If we look at the CUBE expansion on the right, we'll see that given n elements, it produces 2 to the power of n grouping sets. So for 2 elements, it would produce 4 sets, for 3 elements, 8 sets, and so on. Recall that each grouping set is logically equivalent to a union all subquery. So the CUBE modifier saves a lot of typing. As for the query results here, in black color we get total sales grouped by state and year, in blue grouped only by year, in orange grouped only by state, and a single red row for the grand total. Now let's turn our attention to window functions. Window functions are supported by virtually all database systems. They provide a concise way of specifying aggregations over logical data partitions and windows over those partitions. Let's start with a simple window function called computing rank over the whole collection. We'll use the rank function for that, followed by over subclause, which indicates a window function call. Inside the over subclause, we are providing an ordering condition. Window function evaluation in this case is the following. First, we establish the input tuple stream. Our product dataset contains a small number of documents with non-numeric values of list price, so we need to filter those documents out. Then we start processing the over subclause. We order all input tuples by their list price from greatest to least because we have a descending modifier in the order by. Then we go through those ordered tuples one by one and assign their rank, incrementing from 1. If a product has the same list price as its predecessor in this order, then we do not increment the rank. We skip over that rank value until we find the first non-equal successor. That's why there is a jump from 5 to 10 in the rank value of the last item. The previous query was computing rank over the whole dataset, but what if our goal is to establish rank within each product category? We could achieve that by using a partition subclause. The subclause instructs the query processor to partition the input tuple stream into non-overlapping logical partitions, and then evaluate the window function independently on each partition, ordering partition tuples before computing the function. As we can see in the query results, in this case we have multiple products with rank 1 because we started from that value in each product category. Recall also that the rank is the same for product with the same list price. That's why we have 3 top-ranked beverages in the result. Logical data partitioning performed by window functions gives us a flexible way of filtering data within those partitions. In this example, the rank is computed by the subquery and used by the main query to return only top products in each category. Notice that the subquery is written as a common table expression using the with clause. This is another SQL feature that is supported in NoSQL. Common table expressions make queries modular, easy to write and debug. As you can see, we have query results ordered by rank and only get top-ranked products in each category. So far we talked about special window functions like rank, but any regular aggregate function can also be used in a window function call. Aggregate functions, however, need a set of values to operate on. Therefore, when an aggregate function is evaluated in the context of a window function call, there is an additional subclause in the over clause that defines a frame of tuples for it to process. You have probably seen it before in SQL queries. It starts with rows or range and could be bounded, unbounded, preceding or following. It is optional though, and if not specified, then there is a default one that would be used. We support exactly the same frame specification in NoSQL with the same defaults. The evaluation steps are then augmented by an additional frame computation step. The first 2 steps remain the same. The input tuple stream is logically partitioned, then tuples are ordered within their partitions. Each partition is then processed independently of others. Couchbase Analytics is able to process them in parallel using all available system resources. The evaluation starts at the first row of a partition and computes a frame of tuples for that row according to the frame specification. Interestingly enough, the frame may or may not include the row itself because the purpose of the frame is only to provide input values to the aggregate function. Then the aggregate function runs on that frame and computes the result, which is added to the output. After this, the query processor moves on to evaluate a second row in that partition. The frame is recomputed again for the second row, and the aggregate function is re-evaluated on that frame, producing the second result value. Then the evaluation moves on to the third row and so on until the whole partition is processed. Frame specification syntax is quite elaborate and gives plenty of room for query optimization opportunities. A frame could be static, so its content doesn't change from one partition row to another. Some frames could be sliding, while others can have a fixed starting point and just keep growing within a partition. This variety allows the query processor to employ optimal execution strategies for different frames. Coming back to our example, there is no frame specification given in the window function call here. So the sum functions will use the default frame specification, which is range between unbounded preceding and current row. So this frame corresponds to a running total computation. The query intent is to produce monthly sales in 2021 along with their running totals. In order to achieve that, it first aggregates sales by month and then uses the window function call to compute running totals over those aggregated values. And one more query example before we move on to user-defined function. This is a very common analytical query. We would like to produce a report showing our annual sales growth broken down by quarters. In other words, how our sales are doing each quarter this year as compared to the same quarter in previous year. In order to produce this report, first we need to aggregate orders by year and by quarter within each year. That's what the subquery is doing. Then it's time to apply a window function on top of those aggregated values to compare each quarter with its predecessor from last year. The window function we'll use is called lag. It provides access to a previous value in the logical partition produced by the partition by subclause. That's exactly what we need here to solve our problem. We partition subquery results by quarters and order by year within those partitions. Then we use the like function to access the previous sales value, which is the quarterly sales in the previous year. Once we have that value, the rest is straightforward. Notice that we have now for the first sales growth number in the query results. This is because we only have sales data starting from 2019. So the like function returns null for the first row in each partition. Hence, our growth computation expression also returns null. User-defined functions allow users to store an expression or a NQL subquery as a reusable function, which can be invoked from ad hoc queries or other user-defined functions. User-defined functions are created by createAnalytics function DDL statement and deleted by dropAnalytics function statement. There is no performance penalty for using user-defined functions because they are inline into the main query during query optimization. In this example, we create two user-defined functions. The first one is products with rank, which assigns rank to each product in the products collection. The second function is called top products with rank. It accepts max rank parameter and returns top products based on the parameter value. The main query then uses the second function to fetch top 3 products in each category. Finally, both functions are removed from the system catalog. This concludes our overview of the advanced analytical features in NQL for Analytics. And for more information, I would like to recommend this excellent book written by Don Chamberlain. It's called SQL++ for SQL Users. And we also have a website that hosts our language tutorial and allows anybody to run sample NQL for Analytics queries. So thank you very much for your time. If you have any questions, please feel free to contact us. So the contact email is available on the screen. Please reach out, and this concludes our session. Thank you.